Thanks. Thanks for being still here. It's tough day, evening. I'm really surprised. Okay, what was the title of my course? Oh, good. There is no cluster, yes, up to now. So the goal of today's lecture is to say something first about cluster, to define what is a cluster varieties, to show how are they connected to stuff which was discussed before. Cluster varieties, that's varieties which with so-called cluster structure, and the structure means that this variety is glued from chart, and each chart we have some good fixed set of coordinates. In terms of Poisson geometry, these coordinates are very close to Darboux coordinates. And also we have some control about transition maps between different charts. They're more or less as simple as possible. They're not monomial, but they're given by more or less like binomials. Each chart on such cluster variety is correspond to object which is called seed. So let me define this. Okay. I used to separate in 3 parts, not in 4, but I don't know what's the reason. Definition. A cluster seed is following data: I and F epsilon x. And this x is bold. Where? So I is usually finite, but theoretically not necessarily set. And IF is a subset of I, which is a so-called frozen subset. Epsilon is anti-symmetric matrix. Epsilon is equal to epsilon ij, anti-symmetric matrix. So this indices I and j belongs to the set I. So the set I labels rows and columns on the matrix epsilon, and as I said, anti-symmetric, so epsilon ij plus epsilon ji is equal to 0. And also it is assumed to be almost integer. So in examples which we will have and usually have, these numbers are either integer or half integer. And if both I and j are integer, then epsilon ij is. If both I and j are unfrozen, then epsilon j integer. So if there are no frozen vertices, then epsilon j are just integers. And what remains? Remains x. X is a set of variables xi, where I belongs to the index set I. And this axis would be a local coordinate on a chart. So, bunch of data. So among this data, we can see that first part is set, subset, and then some matrix integer value or half integer value is some sort of discrete data, or if you want combinatorial data. And X are local coordinates. X are algebraic to analytic local coordinates. It is usually convenient to think about this combinatorial data graphically. Namely, encode this combinatorial data in terms of quiver-oriented graph. So we can, for this I, let me maybe give example and then, so let's pick the following. I don't know why, but I prepared matrix 6 by 6. Okay, you assume this matrix is antisymmetric. It is already sufficient, but maybe still. Okay, so this is a matrix. You can see that we will assume. I will assume that frozen vertices are 1, 2, 5, and 6. So in unfrozen part, which is this, we have no half integer values, so condition satisfied. And now how we draw corresponding quiver. So in the quiver, actually, maybe not. Maybe I want to be to 1, 3, 4, and 5, 6, like this, whatever. And in the quiver, so we have vertices of quiver would correspond to the set I. Some of the, and if vertex is frozen, it means that the corresponding index belongs to the frozen subset. Then we will draw a square. And if unfrozen, we will draw a circle. In this case, so we have 6 vertices, something like this. Let me label them. So this would be 1, 2, 3, 4, 5, 6. Is yellow color visible? No? This is the first day of the school. Do we have, what's the experience? Is any color visible? No? So just do white. Okay, I see. 1, 2, 3, 4, 5, 6. Now what's written here? So epsilon ij encodes number of arrows from I to j minus number of arrows from j to I. Okay, so epsilon 1, 2 is minus 1. It means that we have arrow from 2 to 3. Epsilon 1, 4 is 1/2. It means that we have arrow from 1 to 4, but this is a half arrow, so it means that I draw it dashed. So 1/2 correspond to dashed arrow. What else? Epsilon to 1 is already used. Epsilon to 3 is 1. So here, this is with 4. So here, 0, 0. What epsilon? This is already used. Epsilon 3, 5 is 1 here. What else? Probably this here, here. And probably also some additional dashed line. Which one? Maybe this one. Some example. Okay, it agrees with what Relton was pictured in my notes, but doesn't necessarily prove that everything is correct. Okay, so usually we will think about combinatorial data in terms of quiver. So set of I is just set of vertices. I have a set of rows and vertices, and instead of matrix epsilon, we have adjacency matrix of a quiver. Okay, but this is just one chart. The main object here is a transition map which goes from one chart to another chart. Actually, there are two types of such maps. Maps between seeds. Very simple map is permutation. So we can just permute. We can take any permutation, I don't know, alpha from I to itself, such that alpha map frozen vertices to frozen vertices. Then matrix epsilon will be conjugated by this permutation, and also axis will be permuted by this element. Something like this. So we will not distinguish seeds which are different by numbering of coordinates. This is a standard story when we speak about coordinates. Is it a set or is it an ordered set of functions? It's a matter of, it's usually more convenient to think that this is just a set of functions, so we can renumber them in any way. The most non-trivial definition is a definition of monotrivial definition of mutation. So mutation is a transformation which maps one seed to another, and it can be performed in any unfrozen vertices. Definition. So mutation in unfrozen vertex, which I denote by K, in unfrozen vertex K. So unfrozen means that I without I frozen. Is the transformation, which you denoted by mu k, from the one seed I frozen epsilon x to a new set, and this set has the same sets of vertices. I frozen are the same. Adjacency matrix can change, will be new one. It will be epsilon tilde, and vertices will be x tilde. Okay, and here I left some space to write down formulas for this mutation. But before writing formulas, I want to give an example. So assume that we have a very simple quiver, ignore all without frozen vertices, with just two arrows. We have three vertices with variables, say, A, B, and C, and we have arrows from A to B and from B to C. And we will do mutation in vertex B. What do we get? So I defined seed as a quadruple, so we have a set of vertices, set of frozen vertices, adjust symmetries, and coordinates. So vertices preserved, frozen preserved, so just two data. Adjust symmetrics, namely quiver, and values of the variables. First quiver. So we have still the same three vertices. And we do the following operation. First, we reverse orientation of all arrows adjacent to B. Reverse arrows adjacent to B. B is a vertex where we do mutation. And I'm sloppy and I identified vertex with variable which assigned to this vertex. And then we have to close triangles. Okay, this is quotation marks. It means that if we have some, after this operation, we will have this path of length 2 in center of B, we close it to triangle. So in this case, we add this arrow. And then we cancel double cycles of length 2. So if we have two arrows in opposite direction, we just replace them by no arrow. So this is a combinatorial, transformation is a combinatorial part. And transformation is algebraic part. So here we have A tilde, B tilde, C tilde, and they are equal to the following. So B tilde, variable in which we do mutation, is equal, goes to inverse. A tilde is equal to A times 1 plus B. And C tilde is equal to C over 1 plus B inverse. And that's it. So this is algebraic transformation birational. So since if I work over a field of complex numbers, this can have poles, and even worse, if I work over complex numbers, this can be undetermined. It can be C equals 0 and B equal to -1, and this is 0 over 0. What does it mean? So algebraically, this is can be interpreted. So this, but for generic values A, B, and C, if they are not equal 0 and not equal -1, then this is just one-to-one. This is bijection. So this is birational isomorphism. In terms of algebraic geometry, this can be interpreted some composition of blowups and blowdowns. Actually, it's very simple. Another thing that it is given, so the only non-trivial terms, so here we have some monomial transformations like B to B inverse and multiplication by binomials like 1 plus B. And this actually 1 plus B is the only binomial which we have here. So if you think the simplest transformation are monomials, this is the next one. Okay, now it is example. You can ask how much information do we lose if we just think about this example, and the answer is not much. So write down a formula, but I don't think it will give you much more. So a formula is the following. So B tilde is equal to minus Bij if I equal to K or J equal to K, and is equal to Bij plus or minus absolute value of Bik Bkj minus Bjk absolute value Bki. Sorry. I changed notation at some point from B to epsilon, but with mistakes. Okay, so for the purposes of today's talk, B is equal to epsilon. So what's written here? So the first row is the first rule. We reverse all errors adjusting to the vertex in which we do mutation. And second row means that if we have two vertices which are different from K vertices we do mutation, we keep all errors which we had, but then sometimes we should add errors if we have such triangle. And this factor takes care about such triangles. If I don't, I mean, probably it couldn't be clear from the first glance, and so this is like an exercise, and maybe exercise even harder because I'm not, even if you don't see indices, and the part of the exercise to find indices such that this would work. Okay, and transformation of the variables is also given by the system. So xi tilde is equal to xk inverse if k is equal to I, and xi times 1 plus xk sine of b epsilon ik. No, it wouldn't work. Let me write it a bit better. Xi tilde is equal, so xk inverse if I is equal to k, and otherwise it will be xi plus binomial 1 plus xk, probably xk inverse, which is the same up to monomial factor, and sine of epsilon ik, and this is also in power epsilon ik. So practically, we saw here two main examples. If we have just one arrow from C to B, then it will be multiplied by 1 plus B. In opposite case, 1 plus B inverse. And that's it. Since we mutate only on unfrozen vertices, these numbers are integer, so there's no squares. A standard property of the mutation, so lemma is that m² squared is equal to identity. So one can think about this as some version of reflection, but it's just like version. Another, from the point of view of integrable system, we need to, at least classical, we have to think about Poisson structures. So definition. So cluster Poisson structure is Poisson bracket of xi xj is equal to epsilon aj xi xj. And I want to recall that this is a formula for the Poisson structure which we had when? Yesterday. Up to the difference, perhaps difference between epsilon and b, which can be anything. And so this Poisson structure is called logarithmically constant because it is logarithmically constant. So if you go from xi, you replace xi as exponent of x small variables, then in them you would get xi xj is epsilon to epsilon aj. You can ask, okay, then why you bother us with these capital letters where you have quadratic Poisson bracket? Why don't we work with the logarithms? And the answer is due to mutations. So proposition mu b is Poisson map. So, and if you want more explicit, it means that if we take two functions, two coordinates after mutations, xi tilde sum and xj tilde, and compute the Poisson bracket, then what do we get? How do you think? What this property of Poisson map means in terms of these functions? So we will get Poisson bracket on the new chart. We will get Poisson bracket on this tilde chart. So we will get here xi xj. They should be tilde. Here we will get epsilon aj. And how do you think? Would it be tilted? Should be epsilon tilde in this formula. Maybe if should be clear that should be tilde. So here in the this is a computation. So you take xi tilde xj tilde, substitute these formulas for them, compute Poisson bracket using epsilon, and it appears you will still get product of these functions with the new transformed epsilon tilde. So this logarithmically constant Poisson bracket transforms into logarithmically constant Poisson bracket. But what happens with the logarithm of variables, it's hard to say. So assuming we know logarithm of A, logarithm of A, logarithm of A, logarithm of B, logarithm of C. What is the formula for the logarithm of this guy? Who knows? There's no way to easy formula to take logarithm of 1 plus exponent. So in this sense, the exponents are right coordinates. But since they are exponents, they're not equal to 0. We would rather multiply them than sum. So in this sense, everything is multiplicative. So this cluster structure, they live in the multiplicative world. For example, there is no reason to expect cluster structure in Nakajima varieties, which was subject of the last 2 hours. But you can ask, are there multiplicative analogs of the Nakajima varieties? And the answer is yes, there are. Is there a cluster structure on them? Answer is conjecturally yes. But this is somehow another layer.
that epsilon real is defined to be the assignment of the Poisson bracket after the assignment will be the x.
Yes, yes. So if you know this formula, you can find, if you know a formula for x tilde, you can find epsilon tildes from this formula. But if somebody told you that they're constants, in general, if you just make any transformation, your logarithmically constant Poisson bracket goes to something, not even quadratic, no reason to expect. So this is still a non-trivial statement. But
are designed so that they give up the Poisson structures based in the.
yes, 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 yes.
Other solution to the problem is not the assignment.
Yes. I'm not standard words when people start to talk about cluster stuff. I feel right that people start from saying sorry. I'm not talking as the greatest generality. There are a lot of room to generalization. For example, I started from antisymmetric matrix. Usually, if you want, you can work not for antisymmetric but antisymmetrizable matrix. Somehow encode this like not for simply laced case. Or there are other generalizations. For example, even naive generalization, you can take. So okay, here I defined you one mutation. If you take composition of several mutations, it will be still transformation which preserve properties Poisson brackets logarithmically constant, but it will be not given by binomials. It will be given by some strange functions. And there are other generalizations. Other questions? Okay. Can I talk just for till dinner, or I have others? How much time do I have?
Well, the trains have 10, between 10 minutes and 15.
Okay. I promise that there will be connection between this and Poisson varieties which we had before. Cells and Poisson-Lie group, for example, in GLN. So let me use my 15 minutes for this. So recall that, okay, recall what we had so far, what we had yesterday. So for any element in the product of double while group, we defined GW in G, which is equal to, say, SLN, which was double cell. And actually, we defined some coordinates on this GW by the factorization formula. So if W is a product SI1, SI2, SIL, and this SIs and these indices I1, IL, they correspond to the generators of these two permutation groups. So they are either from 1 times n minus 1 or 1 bar n minus 1 bar. I have two groups or two sets of generators. Then we defined a map EW from C star in some power n plus L minus 1 to actually to GW by the formula E W of X is equal to, first we take some product of Cartan elements, H1, X1, Hn minus 1 of Xn minus 1. And then for each simple reflection, we took corresponding root generator, E I1, and additional Cartan element with additional X. So we have L simple reflections, so we have L root generators, and each of them comes with corresponding Cartan factor. And formulas for this is, let me just draw them. So EI is equal to matrix which has units on the diagonal and 1 unit above diagonal. 1, 1, and 1 above. And zeros everywhere else. And EI bar, which is Fi, is a matrix which has units on the diagonal and 1 unit below diagonal in ith position. And H of X is some Cartan matrix, which maybe I will not recall. Lemma. So as consider simplest non-trivial double Brière cell. So the simplest double Brière cell is a case where W is just identity. Then the corresponding double Brière cell, in this formula we have just the product of Cartan elements, so the corresponding double Brière cell is just Cartan. It is great, but the Poisson bracket on Cartan is 0, nothing non-trivial. So the simplest if we have one reflection. And there are two cases, of course. It can be reflection from the standard indexes or from the conjugated. So consider first G Si bar. So in this case, this factorization map has the following structure. E Si bar of X. So we take this just product H1 of X1, H n minus 1 of X n minus 1, Fi, H I of new variable which I denote by X. And as I claimed last time, the Poisson bracket in this coordinates would be logarithmically constant, but maybe today I'll write these constants. So these constants would be as follows. So Poisson bracket between X and Xi would be equal to Xi. Poisson bracket between Xi and Xi plus minus 1 would be equal to 1/2 Xi plus minus 1. And Poisson bracket between Xi plus minus 1 and X would be also equal 1/2. But actually, instead of this, yes, and of course, to say all other Poisson brackets are equal to 0. But instead of this formula, I prefer to draw a picture. Maybe without this line first. So we have our variables. So first we have a product. So we have x1, then x2, x3. In picture which I prepared, I draw them from, I label them from below. x1, then we have x2, x3, x4, and also additional x. And we have arrows. So here arrow goes in this direction. Here we have two dashed arrows. No, sorry. I want to make this picture clear, so I use a bit more effort. So here I say xi, xi minus 1, xi plus 1, and new variable x. And arrows like this. Here's arrow in this direction, dashed arrow in this direction, dashed arrow in this direction, dashed arrow. No, this picture should be symmetric. And no other arrows, so everything else is incomplete. Here, all vertices are frozen because for each vertex we have some somewhere there's half integer numbers. And another case is if we just take not barred but just standard index Si, then situation is the same. So I just draw a picture. The same, but orientations, all orientations are reversed. Same with reversed orientation. Theorem. Can I state it? I think I can. So let W and W times W be any element in the double while group with and fix some reduced decomposition of it as SA1, SA2, SIL. Then seed, okay, seed corresponding to factorization scheme, factorization for EW is amalgamation of seeds SI1, SI2, SI. I haven't defined some words in this theorem. Yes, it was.
What
what does it mean the square mean there is no arrow the other zero?
This one. Here we have, say, xi, xi plus 1. Here can be, say, xi plus 2. Here xi. So I have all the, but there is no arrow between them. There are vertices, but no arrow. Okay, so here, I wanted to state theorem, not in the last minute, but 5 minutes before, so in order to have time to comment something. So I haven't explained, first of all, what are these seeds SI1 and so on, but this is somehow hidden in the lemma. So seed which correspond to simple reflection with bar, I denote by SI bar, and seed corresponding to this simple reflection, I just denote by SI. So quivers which we draw for just simple reflection, I denote them, and then I state that the quiver which corresponds to any double Bessel is obtained by amalgamation of these quivers. And now what do I mean by amalgamation? I mean that I draw these quivers one near each other, and then I glue them. So each of these quivers live in some picture with lines. So when I write some hi of some variable y, I would say that I label my lines 1, 2, 3, okay, 4, and I put y on ith line. So, for example, let's take g equal to SL4 and consider something like S2 bar S2 W. Then S2 bar quiver would be as I wrote it. And here we have dashed arrows. Here we have dashed arrows, dashed arrows, dashed arrows. So this is S2 bar quiver. And quiver which corresponds to S2 is the same but with reversed orientation. And now I glue them. So I glue these vertices, and these vertices. So I can draw it like this. Now what happens with arrows? Before I had half arrow in this direction and half arrow in these opposite directions. They cancel each other. Similarly, I had half arrow in this direction, they also cancel each other. And this is a quiver. Then if I want to add something else, I draw it here, and then also blue. For example, if I had, let me do one more gluing. If I had S1, then what is S1? I draw this, and this. So in this picture, I had xi minus 1, xi minus 1, xi minus plus 1. But for S1, there is no x0. So this, there is no vertex here. Okay, and the arrows like this. And then I glue them again. So I connect them. And I think again, just cancel, this arrows just cancel. And you can see in this picture, sometimes vertices which you have, they have no longer half integer arrows. They have no dashed arrows. At this point, we can unfroze in vertex and then do mutations. Okay. I don't know how I'm doing this time, but I'll finish this board and stop. Whatever it takes me. Questions? Everything is clear, yes? So in the original, in the quiver which correspond to initial seeds for simple reflection, all vertices are frozen. But if after the gluing, for some vertices, there was no half integer edges, we can unfroze this vertex. So you can glue to. I don't know how to explain. So you have two frozen things, but you glue them, and so logically we think about this frozen vertex as like half of the vertex. But if you glue two halves, then you can glue them and think maybe it's really like honest stuff. Okay, I want to use this board to prove. So proof of theorem. But of course, let's be realistic. Doesn't mean that idea of the proof. 2 steps. Step 1, prove lemmas. And this is computation. It's not computation just for the Cartan where Poisson bracket in 0, but the next possible simple case. It is essentially not SL2 computation, but SL3 computation. This is step 1. And step 2, use Poisson-Lie property of our Poisson bracket. Recall that Poisson-Lie property tells us how to compute Poisson bracket for the product of 2 elements of G times H. And this factorization scheme is actually prepared for the products. So if we know Poisson brackets on one factor and for another factor, which both of them correspond to simple refractions, that we know this by step 1, then we know Poisson bracket for their product. And this is essentially the proof. But I still have place, half of the board. Let me use it. You can ask, where are the mutations? Why bother to use these formulas, promote them? And mutations here, at least partially responsible to the perhaps only non-canonical choice which we made here. It was a choice of reduced decomposition. So another theorem says that if we have 2 reduced decomposition, SI1, SIL, SG1, SGL, then seeds corresponding to seeds SI I1, IL, and seat corresponding to J's, G1, GL, are related by sequence of mutations. So each factorization scheme doesn't give us coordinates on the full double Bras cell. It is so double Bras cell itself defined by some equalities and inequalities. But the image of this factorization, we have more inequalities. We saw it in example yesterday. But it appears we can cover the full double real cell using different factorization schemes, and they're related exactly by mutations. Maybe I don't have space to write proof of this, but I can at least write something. So the change of the reduced decomposition, two different reduced decompositions are usually connected by some braid moves. So typical braid move is something like Si plus 1, Si is equal to Si plus 1, Si plus 1. And in terms of this factorization scheme, this corresponds to the following identity. Ei plus 1, Hi of x, Ei is equal, and now we will have is in opposite in this braid permuted order, E plus 1, Ei. We will have H, and now which would correspond to I plus 1 of the inversed variable. And then we will have also some bunch of H's, some Hi of some argument, Hi plus 1 of some argument. Here also Hi plus 1, and monomial like 1 plus x will be argument here. So this formula for algebraic mutation is encoded in this relation which we have just in Lie group of matrices. What's the conclusion? I defined cluster varieties and at least stated that double Bria cells, they have cluster structure. From the point of view of integrable system, so, point which I tried to make, that we should be interested in some symplectic submanifolds of Poisson manifolds. So, and after KKS Poisson structure, it's natural to look for Poisson submanifolds in Poisson-Lie groups, for example, on these double Bria cells. In order to do some computations, good to have some coordinates, and cluster story gives us very natural coordinates. So now we have Poisson manifolds, we have coordinates on them, but we still don't have integrable system. See you tomorrow in the morning.
Short collection. Short. All particular queries and
Multiplicative. First of all, multiplicative Nakajima queer varieties. No, not once which was defined by Andrei. So typical example of Andrei was cotangent bundle. And I tried to say cotangent is additive in some direction. So it's a spectral bundle.